thank you for the time so I can present my presentation. Thank you, Sensei, and other friends that come to here. So, I want to introduce myself. My name is Muhammad Abdul Haq. You can call me Haki from Indonesia. And my supervisor is Professor Nadia Takawa. So, my research team is sport analysis with the deep learning. So, my title is a residual unit architecture for shuttlecock detection. This is the outline of my presentation. So, there is a pre-introduction, introduction, and the related works and the method until the reference. So, in the pre-introduction, I will tell the story why I chose this research. Okay. So, you can see this is a badminton matches, and this is Ken Tomomoto from Japan and Linda from China. So, why I chose badminton for my research? The first is badminton is the fastest racket sport. You can see the smash of the Ken Tomomoto was very fast in these matches. And number two is every player has a unique play style. So the other player maybe from Japan, from Indonesia, from China, it is a different style, how he smash, how he defend. And the last reason is badminton is second most popular sport worldwide. The number one is soccer. Okay. So also I will tell about my research before I said my research is shuttlecock detection. So there is I detect the player detection like heat map visualization, and I just published in the conference in the journal. And in the last conference, I proposed a residual unit architecture. So I will show you my previous research. So this is my previous research in the first year in the master. So I tried a player. This is Akane Yamaguchi versus An Se-young from Korea. And this is the output of my first year of the master. So this is a heat map, how the player moves in the direction. So let's go to the introduction. So in the tactical analysis of badminton, shuttlecock trajectory is provide essential information. So in this point, that's why I chose a master thesis. It's a shuttlecock direction. So shuttlecock information provide the information to compute hitting timings and other sub-parameters. So extracting shuttlecock trajectory information from the covered badmintons is highly demand or somewhat hard. And several existing works on the shuttlecock detection have been proposed. It was TrackNet version 2. I will explain in the second section. So, due to the depth of the network, so the TrackNet version 2 uses deep learning. It is a network might suffer a well-known vanishing gradient problem. So, what is vanishing gradient problem? Vanishing gradient problem is where the gradients become very small and eventually disappear as they are propagated through the layers of the network. In the network, there is a activation function. There is a zero between 0 and 1, which means that their gradients become very small when the input activation is far from 0. So they are effectively 0, and it making the learning more worse. So we believe there is a room for a TrackNet version 2 to further improve the shuttlecock detection performance. So we propose extend the TrackNet version 2 by introducing residual connection in its flux. A residual connection could mitigate the gradient vanishing problem, resulting in a higher shuttlecock detection performance. So let's go. What is the TrackNet? The TrackNet version 2 is a program to detect a shuttlecock from badminton broadcast matches. It consists of a unit-based encoder-decoder backbone. Unit means the network like a U-shape like this. And you can see there is no skip connection within any convolutional block from here, which could prevent vanishing gradient during training. So this observation motivates me to introduce a residual learning to this network. Let's go to what is the residual network. So recent research has found that a deeper network could achieve better performance. It is better performance. But training such a deeper network become more challenging to the gradient vanishing problem from CCD et al. In 2014. Another researcher proposed the deep residual learning framework, which uses identity mapping to make the meaning clear. So there is a formula behind the residual network. It is like this, y until like this. So the x is the input and y is an output. And f is a function order convolutional block with parameters weight. And the input is directly added to the convolved output. So you can see there is 2x. It's called identity mapping. So this is a method that I use. Sorry if this is very small, but this is the details of my network. There is 4 levels. The first is input. This is encoder. This is decoder, and this is output. And in all networks, there is 18 convolutional blocks. And in every block, this is the encoder level. There is a convolution, there is activation, that's normalization. And in the decoder layer, there is a 3 convolutional. And in the first of convolutional block, there is a convolutional transpose. I will explain about precision, recall, accuracy, and outline. So there is a predicted and actual. So I will explain. The precision is true positive, or true positive plus false positive. If someone didn't know, this is a formula to calculate the performance. So if you see before this, this is a convolutional transpose. So in the TrackNet version 2, they didn't use a transpose convolution. They use a bilinear upsampling. So when we train in the network, the result of performance is different from the first, second, and the third. But after many training, I try to transpose convolution, and the performance is same. So I can do a research more about TrackNet version 2. And if you didn't see the table very well, I have designed and visualized to the better visualization. So this is the input, this is the output, and this is the encoder, this is the decoder, and you can see in every block here there is like a skip connection. It is a residual network that I have explained before. So every block has a residual network to prevent a vanishing gradient problem like this. So let's go to the experiment and result of my research. So we use a public shuttlecock detection dataset to evaluate my proposed method. So the dataset consists of 15 broadcast videos. I'm sorry, this is only 9, but actually this is 15 broadcast video. and 3 game to test. So the dataset contains around 55,000 total frames, including around 46 dataset for training and 9,000 for testing the data. And this is the training parameters that I use. There is a batch size, we use 8, and number of cohorts 16, and this is the input of the image frame. So for the pooling method, I use a max pooling, and there is a convolutional transpose, and this value for activation, and there is optimizer, scheduler, and we use a 30 epoch for the training, and we use GPUs. So let's go to the experimental result and inference. So in the training ones, we can see the blue one is a TrackNet version 2, and the red one is my method. So the loss of the TrackNet version 2 is higher than my proposed method. And for the validation loss, TrackNet version 2 is more loss in this validation. So my proposed method is better in the validation and training. And this is an overall result of my research. So the precision is higher than TrackNet version 2. Also recall F1 accuracy. So in overall result, my proposed method is better than the previous research. So this is in the table. I will show you a picture. So this A figure is a TrackNet, and B is my proposed method. So let's go see the TrackNet. There is a red dot in here. Sorry, it is very small, but because Shuttlecock is very small. So red is a ground truth. Ground truth means the actual position of Shuttlecock, and the green one is a detection result. So the green is detected some way miss. So for example, Shuttlecock is in here, but the TrackNet version 2 detected the head of the player. We can see in the proposed method, it detected very well in here, also in here, and somewhere miss it, and it's detected very well. So the conclusion, so in this research, we propose Shuttlecock detection network that interprets residual learning to unit-based TrackNet version 2 model, and our proposed method performs better than TrackNet. It improves precision, recall, and the other in all aspects. And in the future research, we plan to apply attention mechanism in the skip connection in the network to improve the performance of Shuttlecock detection. Last but not least, this is a reference that helped me to provide this research. The first is the TrackNet version 2 itself, and deeper of convolutional and about residual network. And our research is PyTorch for the framework. Thank you for your time.
So now this session is open for the question.
Thank you for presentation. Please show slide number 16. Yes, very small. My question: what resolution of the image size do you use? What what resolution, please? Oh, yes, yes. This resolution is enough for your application. I think it's a little bit small.
Thank you for the question. So the input frame is 1024 frame. That is. But when I try to train, it is very long time to take. It takes around maybe 4 until 5 days to train, or in the lab. So, and with using this frame, I just need one day to train in the lab. So that's why I think it's better to use not very small, but yeah, but you can see in the result is very acceptable to detect the subtle core.
Thank you.
Slide maybe 18. I'd like to ask about accuracy. Your proposed method provides around 77%. So is this enough for your purpose or application? High enough?
Thank you for the question. So, if I will go to the next slide. So, if we see the result, it is nearly perfect in the 1 and 4, but in the second picture, like a miss. In here, so a little miss, and the third is some like error. So I think it is very good for application, but not very accurate because it's only one camera to detect all video. That's my opinion about my research.
So can you improve the accuracy by changing the structure of the network or any other method?
The future research, I have a plan to apply a attention mechanism. So if we move to the network, in here, this is a key connection. When the network is trained more deeper, but added some data from the first. So it will mix the trained data with untrained data. So I have a proposed method, the next future plan to apply attention in here. So the data will be not mixed to untrained with trained. That's my future research.
I have a simple question. How affect the viewing camera angle to your performance? So I mean that your method can be applicable in the video or captured from the side view or top view.
Thank you for the question. So it looks like hard to applicate because the data set is taken from some badminton video, like from YouTube or BBS. So, and the data set, many data sets are from backside. So I have the very first time in the master, I plan to take a data set from a top, but
I think the view of the shuttlecock is shuttlecock can be rotated in the smashing in the playing state. So I think that this can be applicable any viewing angle. Is that true or false? Could you tell me your opinion?
Yeah, thank you. Maybe it is applicable because it's not only from back view, but from this view, like so, like this side view. So I think it's applicable to other view.
OK. Thank you. じゃあ時間になりましたので以上とさせていただきます。ありがとうございました。では以上で本セッション、終わりでございます。ちょっと休憩を挟みまして、予定通り14時40分から再開といたします。それまで休憩でございます。それまでの間ですね、今次のセッションの方いらっしゃいましたら、接続テストをしていただきますようにお願いいたします。